I'm going to be talking about sort of what Prashant was saying about this kind of idea of meta complexity, but I'm going to be talking about it from the perspective of compression, because it's a very, very natural computational task that is of interest. Given a data set, how much can we compress it, and how do we compress and decompress efficiently, and so forth. And these kind of questions that are sort of fundamental to data compression turn out to have implications for all sorts of other areas of computer science, to machine learning, to cryptography, to complexity theory, to logic, and so forth. And I want to try to give you a sense of the richness and diversity of this area, sort of like an area that's sort of philosophically quite deep, but doesn't actually require all that much background to appreciate. So I'm hoping that the concepts and the questions will be fairly clear to you, but hopefully they will kind of reward kind of further thought and exploration, which I'm hoping this will be occasion for. So here's a kind of rough plan of the talk. I'm going to, first of all, motivate the sort of framework that I'm be talking about. So the talk is going to be about notions of congruent complexity, sort of, which is a notion about the individual complexity of strings. And I'm going to be motivating that as a model of compression, a way of trying to understand how much data can be compressed. And I'll be describing what congruent complexity is, defining it, giving some basic properties, and then telling you about some very interesting facts about it that have sort of consequences for the foundations of mathematics and for computer theory. And then I'll be talking about how to define versions of congruent complexity that have resource bounds on them, where you're trying to do things in a resource efficient way, and about connections that has to the P versus NP problem. And then I'll be talking about applications or connections to learning theory, and then finally to cryptography. And when I'm talking about cryptography, that'll bring us to actually state-of-the-art work that has been done very recently, but which I think is already, at least in terms of the statements of the results, quite accessible to graduate students in any area of computer science. So that's the rough plan. I'm not quite sure what the like the convention is with questions at this research week. I mean, will they be sort of like, can people raise their hands and ask questions in the middle, or is it at the end? Prashant, do you know?
Zesa would know. Zesa, how has it been going on? I haven't been attending really.
Yeah, it's up to you, Rahul. Basically,
okay.
If you want, you know, in the previous talks, people were asking questions on the chat.
Okay.
So either you know, Prashant can read them for you, yes, or you can go back to them after, you know, a few slides. Completely up to you. Yeah.
Okay. Yeah. So I'm just to say that yeah, if Prashant's okay, like when there's a question in the chat, kind of like stop me and read it out. I'm very happy for my talk to be interrupted and to answer questions as they come up. And
okay, I will do this.
Okay,
I'll watch the chat.
Great. Thanks a lot. So yeah, so feel free if there's anything that's not clear to get me to clarify it. And I'll try to do my best to maintain sort of like I mean, to try to get to interesting kind of parts of the talk while still not kind of assuming too much on the part of the audience and trying to cater to a fairly broad audience. Okay, so first of all, the motivation. What's the motivation? So we're interested in data compression. I mean, data compression is obviously a fundamental task in computer science. And this is kind of important from many different points of view. I mean, most obviously from a communication point of view, when you're kind of sending files across, you want them to be compressed so that you can send them across in a way that's efficient, time efficient and space efficient. And we have various compression formats like zip, and we have like algorithms like the Lev-Zempel algorithm and Huffman coding and so on, which allow us to compress data. So that's probably when many, if you think of data compression, if you think about it, these are notions that might be coming to mind. So that's what we often think about when we think about data compression. But I'd like to make the point here that data compression is also connected to other sort of fundamental areas of computer science, to learning, because At a very high level, the main goal in learning is to find a compact hypothesis that explains your training data and performs well in the test data. So ideally, you'd like to get an explanation of the data that you've seen already, and you'd like to get predictions of the data that you will see in the future. That is very much about kind of finding compact explanations, a compact hypothesis, which is about compressing. Is there a way of compressing the training data? And it might be less obvious, but compression is also sort of key to cryptography, because one of the key sort of primitives in cryptography is pseudorandom generators. And when you're sending encrypted data across, this relies on the ability to efficiently produce pseudorandom strings, which look like random strings. You can't really tell the difference easily using an efficient algorithm. But one difference that is apparent, as I'll get into more in that section of the talk, is that pseudorandom strings are compressible in principle, but random strings are not. In a way, compression can tell you the difference between pseudorandom strings and random strings. And if you can do compression efficiently, you'll be able to break pseudorandom generators. So compression is quite closely tied to fundamental questions in cryptography as well. So our goal is somehow to try to establish theoretical foundations for data compression. And we can come at it from different angles. But there's a couple of questions that are very, very natural to ask for any framework that talks about data compression. How do we characterize the inherent compressibility of data set? What sort of like measure of the data set tells you how compressible it is? I'm going to be interested in inherent compressibility. So somehow imagine that there's like some data is compressible, other kinds of data are not, and how do you distinguish them? What sort of features of data make it compressible? And in case data is compressible, is there an efficient procedure to do it? To compress or to decompress, depending on the setting. So you want to be able to recover the data efficiently from compressed data, but you might also want to do the original compression efficiently. And throughout this talk, I'll be concerned with compression that's lossless. I want compression that doesn't actually lose any information at all about the data. When you recover the data, you recover it exactly as it was before you did the compression. So there is sort of a theory of long-standing theory, very beautiful theory due to Shannon, which is motivated by the question of compression and does provide sort of framework for it in a certain setting. So Shannon's theory of source coding provides good answers to the questions that I just mentioned when we have some sort of like a priori distribution on the data. So if you have some distribution on the data, and you want to be able to, and you know that, so say, let's say you have some distribution of symbols and you know that you're receiving several symbols, and you want to be able to compress like the sequence of symbols that you're receiving. By how much can you compress on average? This is something that Shannon's theory provides you a very good answer for. We know that the entropy of the distribution on your data is the optimal expected compression length. This is kind of like a standard result. And there is an efficient compression procedure of Huffman coding which achieves this. And so this is kind of a very clean, beautiful answer for this question, but this assumes that we know what kind of distribution on data we have and that there's a reasonable way to model distributions. So for example, if you have natural language utterances, so like your text consists of words in English, for example, then there's a zip flaw which tells you that roughly speaking, for a certain word, you kind of like, you look at the rank that a word has in terms of its number of occurrences. So let's say that you have the most popular word and then the next most popular word and so on. And let's say that you have a word that's the ith most popular word, then the probability with which it'll occur in a text is roughly proportional to 1 over I. So that's what Zipf's law tells you. So that gives you sort of like a sense of what kind of distribution you can expect on words in your text. And if you have some a priori information of that sort, then Shannon's theory is quite useful in sort of talking about and theorizing compression. But I'm going to be interested in a setting where we don't have any prior knowledge of this form. So we want to be as general as possible. We're not assuming a specific context, such as like natural language processing, where you know such a distribution in advance. And we're interested not in distributions of a data, but about specific fixed data. And it's going to be modeled very, very simply as a finite string. I mean, any finite kind of amount of data you can sort of encode as a binary string. I can assume without loss of generality that it's a binary string. And so the question will simply be, given a binary string, how much can we compress it? Does this question even make sense? And we see that there's a very natural way to make sense of this question, which leads to some fascinating further questions. Okay, so hope things are fairly clear so far. So what do I mean when I talk about inherent compressibility? Well, it's sort of clear intuitively that some strings should be much more compressible than others. I mean, like a trivial example is that a string of n zeros, so like if you have like n, a string of length n and all the bits are zeros, then obviously this should be more compressible than a completely random string where there's no pattern at all in the string. I mean, that's very intuitive. And indeed, explicit redundancies of strings where certain patterns keep reoccurring, they are exploited in commonly used algorithms such as length-perceived algorithms and use variance. And these algorithms implicitly use grammar-based approach to compression, where they're looking at grammars that generate a fixed string, and they're looking at grammars of that form with few rules. And the number of rules of the grammar kind of tells you how compressible the string is. And that's a good way to think about compression, but just not general enough for the purposes of this talk, because that's one way in which strings can be compressible with patterns reoccurring. But there could be kind of other forms of redundancy that are deeper somehow, that are not explicitly based on repetition. For example, I mean, if you're sort of mathematically minded, if you consider these strings over the digits, so or decimals, so 3141592653 and 27182818828. I mean, these are kind of strings that kind of like would immediately remind you of some mathematical constants. And they don't look at all like random 10-bit strings. And is this something that you can sort of take advantage of in compressing? Like the first string is clearly like the first 10 digits of pi, and the second string, first 10 digits of e, the base of natural logarithms. And can you kind of use this sort of like information that these are well-known mathematical constants to compress these strings, especially when the strings get longer and this pattern continues to occur, that it's kind of like the expansion of natural mathematical constant. So I'm kind of interested in deeper forms of redundancy, which can be exploited when compressing. And that's where this notion of congruent complexity comes in and is very useful. So, but just to step back a bit in terms of like laying foundations of compressibility, what do we mean by a compression scheme? So let's fix some finite alphabet sigma, for example, the binary alphabet. And by compression scheme, we mean a pair of functions, so a compressor C and a decompressor D, which are both from strings to strings, such that for all strings over the alphabet sigma, when you compress a string and then decompress it, you should get back the string, right? That's lossless compression. So you're able to get back the original string for every string that you start off with. So the decompressor is the inverse of the compressor. So that's fairly natural. And of course, there's trivial ways of satisfying it. For example, the identity transformation for D and C satisfies this. But you would also like compression, right? You'd also like as much compression as possible to happen. So we're going to impose quite a strong requirement in that the compressor C is close to optimal in some sense, in that like the amount you're compressing, like when you consider certain class of possible compression schemes, you want a compression scheme that's optimal in that class, in that the amount you're compressing by is as close to maximum possible for every string and for every other compression scheme, right? If you take any compression scheme C prime, you want that in your class of compression schemes, you want your compression scheme with compressor C to be compressing by close to what C prime compresses by. So you want C of X to be not much larger than C prime of X, the size of C of X to be not much larger than C prime of X. So this feels like a very, very strong requirement. It's not even clear that it's possible to satisfy it. We'll see that for some natural class of compression schemes, it is possible. And it's already interesting, and it gives rise to quite a deep theory of congruent complexity. I mean, ideally, we'd also like computability or complexity constraints on the compressor and the decompressor. We certainly won't be able to recover the original data easily. So we can impose the requirement that the decompressor D is computable, or even more, that is efficiently computable, say in polynomial time. And ideally, we'd like that C is computable as well, and C is efficiently computable. But satisfying all three of these conditions turns out to be a really, really hard thing to do. It's not, it's not clear whether any natural compression schemes that do that. So we're satisfied with two of these, and we'll be prioritizing the optimality constraint as much as possible, because we're very interested in like inherent compressibility. How much is a string compressible? And that corresponds to this first item. So we're going to define a measure, congruent complexity, which many of you might have seen before, but yeah, now motivating from the point of view of compression. And this captures the inherent compressibility of a string. Okay, so how do you define congruent complexity? So hopefully I'm not assuming anything here that you haven't seen before. If you've done a basic computability course, you would have seen universal Turing machines. And let's just pick some fixed universal Turing machine U, and it actually doesn't matter which one you pick, just pick like a reasonably small universal Turing machine. And the notion of congruent complexity isn't going to depend very much on the universal Turing machine, only by constant terms. So we can fix some universal Turing machine and not worry about it afterward. And we define this quantity K of X, which is the minimum over all programs P, such that U on the program P and the empty string gives X, right? So universal Turing machine takes two inputs, a program and an input, and it simulates a program with the input and gives you the answer. So in this case, the input is empty. Epsilon is just the empty string. And we're essentially interested in the size of the smallest program, which starting off on a blank tape, starting off with no input whatsoever, produces X. So how difficult is it to produce X from scratch for a universal Turing machine? That's what K of X is measuring, right? So how difficult in the sense of how large a program do you need to be able to generate X starting from an empty string? So K of X is the size of the smallest program that produces X when run with the empty string. So that's a fairly easy definition to understand, I think. And a couple of examples which sort of illustrate how it could be useful for our purposes in terms of establishing foundations for theory of compressibility. So one example we were thinking about was a string of all zeros, and we wanted that to be very compressible. And indeed, K of 0 to the n, where 0 to the n is a string of n zeros, is at most log n plus order 1. So when I use order notation here, it just means as a function of n. So there's some constant which doesn't depend on n. And why is this? Well, in order to show this, all we need to do is to give some program that's of size log n plus order 1, such that this program on the empty string, the universal machine is going to output 0 to the n, right? And we can do that, so informally, by describing n itself in binary using log n bits, or seeding of log n bits. And order 1 bits to describe a program which, given the description of n in binary, will just get the unary description, this 0 to the n, and then just output that, right? So that's a fixed length, fixed size program, which given n in binary, transforms it to a string of n zeros and outputs that. And if we give that, if we describe that program together with n, then we'll be able to get 0 to the n, right? So as we want, K of 0 to the n is fairly small in general. And for special kinds of n, it could be much, much smaller, because it might turn out that n itself is very, very compressible. In that case, it's will be much smaller, but in the worst case, it'll be at most log n plus order 1. Another example we had was the string, the prefix of pi. And let's consider like the string consisting of the first n digits of pi. Let's call that pi sub n, or the string consisting of the first n bits of pi. What is the congruent complexity of that string? It's also at most log n plus order 1. Because again, all you need is to describe n, using its binary representation, which is of size log n, and then a program which runs a program computing pi to the desired level of accuracy until you get the first n bits from it, right? So pi is a computable constant in the sense that it can be approximated to any desired level of accuracy by a Turing machine. So you can specify with constant amount of information the code of a Turing machine which computes pi to any desired level of accuracy. And then by specifying n with log n bits, you're specifying how many bits of accuracy you need. You're able to get the first n bits of pi and output them. And so you get the same upper bound for the congruent complexity of pi sub n as we do for 0 to the n. So this is nice. I mean, 0 to the n, like using like a grammar-based compression approach, like Lemperzer and so on, you'll also get like a bound like this. But yeah, but that kind of approach, I don't think would work to give you a comparable bound for pi sub n or other kinds of compressible or non-trivially compressible information. So here, so these are a couple of interesting upper bounds in congruent complexity and on compressibility. And as we'll see soon, our intuition that a random string should not be compressible will also hold. And there's a very simple argument for that we'll see soon. Okay, hope that things are fairly clear so far and understandable. Stop me if you have any questions. Okay, so just like to describe a couple of like basic properties of congruent complexity, quite elementary properties. One property is that, well, it's going to be well defined and it's going to be at most the size of a string plus a constant. And that's just because it's sort of a trivial program which just copies its input onto its output, right? So like you can describe a string x just by giving x itself. And then the code of a program just copies x and outputs it from the input tape to output tape and outputs it. So any string x can be described by x itself because the program just prints x out. And so the total length of the description will be size of x plus order 1. So every string x has congruent complexity at most size of x plus order 1. Now, how about lower bounds? Well, by simple counting argument, this is sort of a property that you'd expect any notion of compressibility to have. There's going to be like a string of length n such that it's incompressible, that the congruent complexity of x is at least n. And this is a very straightforward counting argument. For any I, there are at most 2 to the I strings of congruent complexity I, because every string of congruent complexity I corresponds to some program of length I, such that u on that program together with the empty string outputs x. And there are at most 2 to the I programs of length I, and each one can output at most 1 string. So there are going to be at most 2 to the I strings of congruent complexity I. And just by summing over I from 0 to n minus 1, you get that at most 2 to the n minus 1 strings of congruent complexity less than n. And by the pigeonhole principle, we know that there are 2 to the n strings, n-bit strings, and there are at most 2 to the n minus 1 strings of congruent complexity less than n. So there's going to be like a string x of length n, which isn't going to be in the set, and so there's going to be it's going to have congruent complexity at least n. So in fact, and you can sort of strengthen this to say that at least half the n-bit strings will have congruent complexity at least n minus 1, and there are even stronger versions of that. So so what we've done here is sort of like we've defined this kind of complexity measure of a string. It's a complexity measure of individual strings. It's congruent complexity. And how does this relate to our sort of framework using compressors and decompressors? Well, congruent complexity implicitly defines a compression scheme where the compressed version of x is this program, right? Like, so you have the smallest program which produces x. That's going to be the compressed version of x. And then to decompress x, all you need to do is to run the universal machine on this program and the empty string, and that'll be your decompressor. It's not clear how a compressor would work. How do you find the smallest program? That's not clear. But the decompressor would just sort of run the universal machine on this compressed representation P together with the empty string, and it'll give you x, right? And then the amount you'll be compressing by is, well, x minus k of size of x minus k of x, because you're going to be compressing to length k of x, and your original length was size of x. So the notion of congruent complexity implicitly defines a compression scheme. And if you recall, we had these three sort of properties that we wanted. We wanted the compression scheme to be optimal or close to optimal. And ideally, we wanted the compression scheme to be sort of to have an efficient compressor and an efficient decompressor, or at least computable compressor and computable decompressor. And we said we were going to prioritize the optimality property. So it is indeed true that for any compression scheme with compressor C and a computable decompressor D, the Kolmogorov complexity of X is not going to be much larger than C of X plus order 1. So it's going to be within a constant term, constant additive term of the compression according to any compression scheme, as long as the decompressor is computable. And that's not very hard to see because D is computable. There's going to be some program of constant size that computes it. And so every X can be described by the compression of X according to this compression scheme, C of X, together with this program P, which is of size order 1. This program P computes D. And then given these two given C of X and P, you can just run P on C of X and you'll get X back, right? So that's going to be a program that produces X. And that program has size at most size of P plus size of C of X, which is going to be size of C of X plus order 1. And so that's going to be a specific description of X according to universal machine. So in particular, K of X is going to be at most C of X plus order 1. So this requirement that looked very, very strong, that we wanted our compression scheme to be so strong that it could simulate any other compression scheme and not be much worse than it, is indeed satisfied here when you're considering a class of schemes with computable decompressors. So the definition of complexity is very, very simple, but this property that you get is extremely strong, and this property is useful in many different contexts. So as I mentioned, well, Kolmogorov complexity corresponds to a compression scheme where the decompressor is implemented by a universal Turing machine. I mean, the compression is the program, and the decompressor runs a program to output X, and that's how you decompress. But how do you compress, right? So that's closely related to the question of, is Kolmogorov complexity computable? Like we have this nice property, the maximum to which you can compress any string X is roughly K of X. That's what we got by this near optimality here. And that is one of the things that we wanted from our notion of compressibility, that we are able to characterize how much we can compress a string to. And there's like a nice unambiguous way to do this here. But the other thing we're interested in is, well, how do we compress, right? Can we compute how much we can compress a string? Given a string X, can we compute how much we can compress it? And the answer, unfortunately, is no. But the proof that the answer is no is very, very elegant. And so I'd like to tell you about that. I think it's something that's very good to know. Yeah, and it'll have some implications that I will soon spell out for the foundations of mathematics as well. Just one kind of remark I want to make here is that, like, we're going to be proving that Kolmogorov complexity K of X is uncomputable. And in particular, what this will prove, what this will also imply is that there cannot be a computable compressor, right? Because if there are a computable compressor, then you can use the compressor to measure K of X, because you just look at the size of the string that the compressor produces, and that string will have size K of X, right? So if there was a computable compressor for this compression scheme corresponding to Kolmogorov complexity, then you could also compute K of X. So if K of X is uncomputable, it also means that there cannot be a computable compression scheme. So like we would ideally like to have a computable decompression scheme, computable compression scheme, and optimality, but this particular plan is not going to work out here. But it's going to have interesting consequences, the fact that Kolmogorov complexity K of X is uncomputable. And I think a nice way to think of this is a version of Berry's paradox, sort of like one of these logical paradoxes. One of the intriguing things about the foundations of computer science is like the close link to all these logical paradoxes. The liar paradox, which is used on the proof of Gödel's incompleteness theorem. Now Berry's paradox, which is going to be closely related to the proof that Kolmogorov complexity is uncomputable. So what is Berry's paradox? It's a paradox about descriptions. So it was described by Bertrand Russell based on kind of an argument due to a librarian called Berry. And it was about considering this expression. The smallest positive integer not definable in under 60 letters. So if definability has a clear meaning, and we might naively think that definable has something with a clear meaning, right? Because you could define integers like, well, the sum of 1 and 2, or the integer with the smallest integer with 5 ones and 3 twos. I mean, there are various ways of describing or defining integers. So it might seem that definability is an unproblematic notion. And what Berry's paradox is going to show is that it's, in fact, problematic in a way it's not obvious at first. So there's this expression, which, well, if you count it, it has 57 letters. So if it was a case of definability has a clear meaning, you're going to get a contradiction out of it. Because if it's a case that this sort of defines some integer n, and n is the value of this expression, because n is the value of this expression, n will satisfy this condition that it's not definable under 60 letters. Because after all, we want the smallest positive integer not definable under 60 letters. So n will satisfy the condition that is not definable under 60 letters. But this expression itself is a description of n, and it has 57 letters. And so that's going to be a contradiction, because we've just said that n cannot be described under 60 letters. So what went wrong here? What went wrong was the assumption that definability has a clear meaning when considering expressions such as the above. And so this is a sort of a logical paradox, which is about assuming that something had a meaning, and it turns out it can't have a clear meaning. But it's very, very closely related to the argument shows that common complexity is uncomputable. And I thought it would be useful to illustrate it first with Berry's paradox, which is sort of easier to see. Then we can see how that corresponds to the uncomputability argument for common complexity. So how does the argument for common complexity go? So I'll first give you the mathematical argument and then describe how it's essentially Berry's paradox. Suppose, for the sake of contradiction, there's some Turing machine M that computes K, that computes common complexity. Well, so what does that mean? That means it's a Turing machine that given X is going to output K of X. And there's such a Turing machine M. We can easily define a Turing machine N that just simulates M and accepts if M outputs a value that's at least N, right? So you can define a Turing machine N that accepts X if and only if K of X is at least N, just by using this assumed Turing machine M and sort of accepting if and only if M outputs a value that's at least N. Now, as we argued, one of the two basic properties of common complexity is that for every length n, there's going to be at least one incompressible string of length n. It's going to be at least one string that has common complexity at least n. So this Turing machine n is going to accept at least one string of every input length. Right? For every input length n is going to accept at least one string x of length n. And now let's define a sequence of strings of length n strings. So x sub n will be of length n as follows. And here's where the similarity to Berry's paradox comes in. It's going to be x sub n is going to be the lexicographically first string. So in some fixed order of strings, say the lexicographic order, you can sort of the first string that n accepts. Okay, we know that n accepts at least one string for each input length n, and so there's going to be a first such string lexicographically, and that's what x sub n would be. And now we just consider the common complexity of x sub n. Now there's sort of like a natural way to compute x sub n. If you're given what n is, then you can compute x sub n by just simulating n, the Turing machine n, for incompressible strings on strings of length n in lexicographic order, and opting the first such string it accepts, right? There are 2 to the n strings. You just simulate them in order. On each string n either accepts or rejects. We know there's at least one string on which it accepts, and we're just going to output the first such string. That'll be x sub n, right? So that's clearly a way to compute x sub n. And in order to do that, you just need to know what little n is, and that can be described with log n bits using the binary representation of n. So what this implies is that k of x sub n, the common complexity of x sub n, is at most log n plus order 1. You just need the description of n in binary plus the description of this constant sized program and capital N, and which is order 1 bits. And so in general, you get a k of x sub n, it's at most log n plus order 1. But what's this other property of x sub n? X sub n is a string that n accepts, and n only accepts a string that has congruent complexity at least n, little n, right? So in particular, that means that for each x sub n, k of x sub n is going to be at least n, little n for each n. But this is a contradiction for large enough n, because log n is a slower growing function than little n. So as the n gets large enough, these two properties cannot be true at the same time, and we get a contradiction. So why is this the same as essentially as Berry's paradox? It's because like essentially the x sub n is playing the role of the first sort of like incompressible string, and just like Berry's paradox is about the first undefinable string, this is about the first incompressible string. And the fact that they assumed that there was a Turing machine for incompressibility, and that's what led to a contradiction. So that assumption must be flawed, and that implies that that in fact congruent complexity is not computable. Just as we assumed there must be a meaning for definability, and that was the flaw in the logical paradox here. The assumption was that there's some machine for compressibility and incompressibility, and that was the flaw in our argument. I think there might be a question.
Yes, there is a couple of questions here. So let's take a minute. The first one is, can you remind us why any computable function such as n or m here only adds a constant additive factor to the fundamental?
Okay, thanks. So the reason is that, so if you take so a Turing machine such as capital M or capital N can be described as like a fixed length program, right? It's a program, it's some fixed program. So think of Turing machines as like programs in programming language. So a Turing machine corresponds to a program, and any program has a fixed length. The point is that this program, the length of the program doesn't depend on the input of the program. The program might get some input, but the length, how you describe the program is independent of that input. So it's some constant that's independent of the input that the program gets. So these Turing machines, capital M and capital N, will get input X, and X can grow as large as possible, but they themselves have descriptions that have size independent of N. And that's the point. That's why order 1, because it's independent of little n, which is the size of the inputs to little capital N and capital N.
And the second question is, doesn't n need a description of m as well?
Okay, that's a good point. Yes, you're absolutely right. But capital M has like a constant size description, and capital N needs a description of capital M. But still, it's all. So I'm thinking of all of them as constant size, which is what we're really kind of exploiting here. That there's only a constant amount of information, and as little n gets big, then that's where you get a contradiction from. Yeah, it's true that capital N means capital M, but all of it is constant size, independent of little n, which is the parameter that keeps growing in our argument.
So there's a follow-up to the first question. In the current slide, if capital N is trying to simulate all little n bit strings, doesn't it need O of log little n size?
Oh, so capital N by itself has constant size, but okay, so yeah, so there's maybe something that is implicit in my argument, which I should make explicit, make things clearer. So when you're computing x sub n, and you're showing the k of x sub n as most log n plus order 1, you're giving some program P to the universal Turing machine, right? That program P is going to consist of a description of n in log n bits, together with a description of capital N in order 1 bits. So capital N won't need little n. It's just this program P which describes x sub n that'll need little n in binary, as well as the code of capital N in order 1 bits. And that's why I get log n plus order 1. That clarifies it.
Okay, seems like it's clear.
Okay, great, thanks. Okay, so yeah, so that's sort of like an interesting kind of argument, I think, a sort of diagonalization, but fairly simple logical argument, but yeah, sort of surprising and maybe not so intuitive at first. Okay, so that's interesting in itself, but now I'm going to show you how to, just like with an additional twist on this argument, how to get like some very interesting consequences for the foundations of mathematics. So yeah, this may be like a little bit of a digression, but I think it's very interesting, and it shows like the sort of like the broad reach of congruent complexity and this way of thinking about compression. And basically, this application is to proofs and to the question of provability of theorems of mathematics. So many of you might have heard of Gödel's incompleteness theorems, which essentially say that, like, if you have a system, a proof system like piano arithmetic, any system that proves mathematical theorems about the natural numbers, there's no such a sound, consistent system which can prove all truths about the natural numbers. And just to be a bit more formal, what it says is that there's no consistent proof system that's effectively axiomatizable. So this is just like a natural requirement in proof systems, that you can check whether a proof is a proof in a computable way, which any reasonable proof system has, right? Given a proof, can you tell it's a proof? Is there a Turing machine which, given a proof, can tell whether it's a proof? Any reasonable proof system is going to have that property. That's what it means for a proof system to be effectively axiomatizable. And the other property that we need of a proof system is that it's consistent, that it shouldn't prove something and its negation. But obviously, any proof system that's we're going to consider, we only want to consider consistent proof systems, because inconsistent ones are useless. They can prove both a statement and its negation. So these are both very reasonable properties. And Gödel's extraordinary theorem says that no such proof system, which is consistent and effectively axiomatizable, can prove all true statements about the arithmetic of natural numbers. So just statements in the first order theory of natural numbers, not all such statements can be proven by proof systems of this form. And it sort of gave, like, I don't know, like a killer blow to this program of Hilbert, which is to effectively axiomatize all of mathematics. Can we kind of find like axioms that allow us to prove all true mathematical theorems? And Gödel's theorem says that, that no, we can't in any reasonable way. And Gödel's original proof of this was fairly complicated, and was actually inspired by the liar paradox. So again, this connection to logical paradoxes. And it turns out that we can get very strong incompleteness results, which in some ways go even beyond Gödel's result, by arguing about common-law complexity, and by doing this in a similar way to how we show that common-law complexity is uncomputable. So I want to tell you about that next, because I think it's philosophically very interesting, but also I think it says something about kind of barriers to doing mathematics in general. So so calling this like the deep intractability of common-law complexity. Common-law complexity seems a very natural notion of compression, but its notion of compression is going to be very hard to analyze in a rigorous way. So now, and this theorem is due to Chaitin from the 60s. So now we're going to consider a proof system that's, again, effectively axiomatizable and sound, which is another reasonable property to require, which is that it only proves true things. It never proves a statement that's false in natural numbers. And we want our proof systems to be sound. Now, if X is a proof system that's effectively axiomatizable and it's sound, then there are only finitely many statements of the form that K of X is greater than or equal to M that can be proven in X, right? So, which is a very strong thing to say, because like basic property number 2 of common-law complexity is that for every n, there's a string X that has common complexity at least n. And in fact, like half of n-bit strings are common complexity at least n minus 1, and at least 3/4 of common complexity at least n minus 2, and so on. So there's infinitely many statements of the form common complexity is at least some number that are true and can be seen to be true in kind of a simple way. But if you want to prove individual statements of this form, there's only finitely many that any fixed axiomatizable, effective axiomatizable sound proof system can show. So even if you consider very, very powerful proof systems, they're inherently limited in their ability to prove kind of low bounds on common-law complexity. And the argument is very similar to the one that we've just seen. Again, like relying on the version of Berry's paradox.
And again, one question before you go to the proof. Sure. There's a question about what the term effectively signifies.
Okay, thanks for that. So this is sort of a historical artifact, I think. Like effectively axiomatizable essentially means computably axiomatizable. That might be like a better term for it, so a proof system consists of axioms and rules of inference, where you use the axioms to generate new theorems, right? And this process, all of it should be implementable by a Turing machine, like in the sense that given a proof, you should be able to tell whether this proof is correct or not in the proof system by a Turing machine. That's what effectively axiomatizable means. So if X is effectively axiomatizable, it means there's some kind of like Turing machine, let's say V for verifier, which given a proof, like a claimed proof, well, says yes if it's a correct proof of a theorem, and then it's able to say which theorem it's proving. And so we just want that to be doable by a Turing machine. And if you take any proof system that we use in practice, like, I mean, certainly like automated theorem provers, but even like very rich proof systems like piano arithmetic, given a proof, you can tell is a proof. I mean, that's the essence of a proof system. And here it just means that you can be able to tell it using a Turing machine. So you are, in fact, allowed a lot of power in terms of checking whether proof is a proof or not. Like proof systems will be considered in practice have much stronger properties than are required here. Okay, so so how does this argument go? So again, suppose for the sake of contradiction that there are infinitely many statements of the form k of x is at least m that are provable in X. So this just means that for infinitely many like x and m, that's the statement of the form k of x greater than equal to m that's provable in X. So there are and by this there are infinitely many m for which some statement. Well, okay, so actually I should be a bit more careful. I mean, I should have said there are infinitely many m for which such statements. There are only finitely many statements of this form. Finitely many m for which such statements can be shown. So I was a bit careless when formulating this slide. There are only finitely many m for which statements of the form k of x greater than equal to m can be shown in X. So suppose, for the sake of suppose instead that there were infinitely many m for which such statements are provable in X. Well, again, you kind of like use kind of an argument to show that suppose we were given m and we can describe m by the binary representation of m in log m bits, then we can computably find an x such that k of x is greater than equal to m is provable in X. And we can do it just by using the effective axiomatizability, the fact that proofs can be checked computably, just by like enumerating potential proofs of such statements in parallel. So we just like for all kind of possible x's in parallel, we try longer and longer potential proofs of such statements until we find a proof of a statement of the form k of x greater than m that's correct, right? Because we have, since the state system is effectively axiomatizable, there is a Turing machine we can check whether a proof is correct or not. So we just try possible proofs and in parallel, trying longer and longer proofs for like x in some order in parallel until we find an x for which the k of x greater than equal to m does have a proof in capital X. And we will be able to find such a proof because of our assumption that infinitely many m for which this is provable in X. But how much information do we require to specify X? Just log m bits together with this machine, this procedure, which can be described with order 1 bits for finding the proof, right? So, and that also finds X. So this X is going to have like polynomial complexity at most log m plus order 1, just as the previous slide. But this X that you find, well, you're going to be proving in capital X in the proof system that k of x little x is at least m. So that means that since the proof system is sound, k of little x should be at least m. And so it's true that k of little x is at least m, but on the other hand, we just prove that k of little x is at most log m plus order 1. And for large enough m, there's going to be a contradiction again, right? So it's a very similar argument. It's just that here, instead of assuming the polynomial complexity is computable, we just assume that the infinitely many m for which such statements are provable in capital X, and you get a similar contradiction. But this is, yeah, it's a very strong statement. It has a simple proof, and it's quite non-intuitive. So it's like polynomial complexity seems like such a natural notion for compressibility, but it's very intractable in a very deep sense for like even extremely strong proof systems. And it's a very, very interesting fact.
Can we show something like this for just consistent proof systems that may not be sound?
I think that might be possible too, but I haven't like thought about it. I think it should be possible to do it, but yeah, I'm not 100% certain. It should be possible though. Okay, so I'd just like to give like a few takeaways from this, like just to recap, because I think we've seen the motivated polynomial complexity. We had like, how is it a compression scheme? What kind of compression scheme is it? Does it sort of satisfy the kinds of requirements we wanted of a compression scheme, and then we described its properties and then non-computability. So we've gone through quite a lot of material actually over the past like 25 minutes. So I'd like to provide like a short list of takeaways. Well, takeaway one, Kolmogorov complexity requires a very natural measure of the inherent compressibility of a string. And it does have this near automaticity property, which makes it very appealing. However, it's not computable. And as a consequence, the corresponding compression scheme does not have an efficient compressor or even a computable compressor. So that's a drawback because ideally we'd like schemes which have compressors that are computable or efficient. But going beyond that, I mean, Kolmogorov complexity is not just relevant to compression, but it's actually relevant to foundational questions about mathematics. It gives like an infinite class of statements, I mean, that are just unprovable, very natural statements. I mean, so like for Gödel's theorem, if you know about the proof of it, the statement isn't all that natural. And statements saying that the Kolmogorov complexity of a string is at least something are very natural statements. And for any large enough m, given a proof system X, there's going to be like some fixed m for which you can't show low bounds for any string. On the Kolmogorov complexity, there's going to be at least m, which is quite a striking fact. So Kolmogorov complexity goes deeper. Okay, so now we're going to talk about resource bounded variance of Kolmogorov complexity. So as I mentioned before, Kolmogorov complexity is not very useful in practice for data compression because, well, a couple of reasons. The decompressor is computable, but it doesn't have an a priori time bound. The universal machine can kind of like run on the compressed representation and produce X, but we have no time bound on how long it should be running. It can run for like astronomical amount of time. That's one issue. But then of course, an even worse issue is that the compressor isn't computable. So like we can decompress data computably, but we can't compress data computably. So this motivates us to consider versions where the decompressor is more efficient. So let's consider like some fixed polynomial time-bound t. Then we can define a time-bounded version k superscript t of Kolmogorov complexity, but just like a simple twist on the definition of Kolmogorov complexity. Like k superscript t of x is just a minimum size of program such that the u of p, so this should be u of p together with the empty string, u of p together with epsilon, the empty string, is equal to x in at most t of size of x steps. So you produce x, but you also do it in time at most little t of size of x. And that's a constraint that we impose. We impose a time bound on how long the universal machine can run to produce x. And now if you look at the corresponding compression scheme and what the decompressor does, it runs in polynomial time the size of the source stator, right? Because, I mean, P is a compressed representation. The decompressor is going to run U to produce X, and it's going to run in time at most T of size of X. So that's quite efficient. Okay, so that's nice. But how about this optimality property? Do we still get kind of near optimality with respect to some class of compression schemes? Well, it sort of nearly holds, almost holds. I mean, I think, yeah, in a sense, it's quite satisfactory. And so what do I mean? So there's this proposition that suppose we have a compression scheme with a compressor C and a decompressor D. And like we consider the class of compression schemes where the decompressor D runs in time little t as a function of length of its output. Then if you consider K superscript order of T log T, so if you consider slightly more time, we consider time bound Kolmogorov complexity, but with time slightly more than T, then this is going to be at least as good as any compression scheme where the decompressor runs in time little t, right? So when I say at least as good, I mean that the amount you compress by is at most constant term away. And it's at least as good with respect to the class of compression schemes that run in time little t. And the proof is exactly the same as before for standard Kolmogorov complexity. And we just need to use now that instead of just that there's some universal machine, we use it as a time efficient universal machine that can simulate a time little t Turing machine in time order of T log T. It's a well-known construction and I won't get into it, but that can be done. And that's why I get this order of T log T term here. So yeah, we don't quite have the same optimality properties before where it was optimal within that same class of compression schemes with computer decompressor, but we do get kind of like an almost optimality, which is still fairly satisfactory. But how about the complexity of compression? So time-bound complexity yields like nearly optimal compression scheme with polynomial time decompression. Nice properties. But can compression be done in polynomial time? This will make the compression scheme ideal for use in a resource-bounded world, such as the one we live in, where we want to do things efficiently. For unbounded overall complexity, we could prove, using a version of Berry's paradox, that compression could not be done efficiently or even computably. So you could prove a very, very strong impossibility results about compression. However, this proof doesn't directly carry over to the resource-bounded setting. And in fact, the question of whether a compressor can be made efficient is closely tied to the NP versus P problem, which is like perhaps the main problem of theoretical computer science and one of the main problems, open problems in mathematics. So if you recall, the NP versus P problem asks whether every computational problem, which is polynomial time verifiable solutions, can also be solved in polynomial time. So for example, the satisfiability problem by asking, is there a satisfying assignment to a Boolean formula that has polynomial time verifiable solutions, but can we solve satisfiability in polynomial time? Or the traveling salesman problem, or the clique problem, or integer linear programming. I mean, there's like all these problems which are in NP but not known to be in P. I mean, this is like a very, very hard question, the main question of computer science, and one of the 6 unsolved Clay millennium problems about at the turn of the millennium, 2000, this list of 7 problems that the Clay Millennium Institute came up with, of which one, the Poincaré conjecture, has been solved, but the other 6 remain unsolved, each one with $1 million prize, and NP versus P is one of them. And this problem turns out to be closely connected to the question of whether the K superscript decompression scheme has an efficient compressor. So how does this connection work? So if NP equals P, then we can show that the scheme does have an efficient compressor. And the way you do that is just, well, you can sort of like guess the smallest program P for which U of P outputs X within T of size of X steps, and then verify that that's the smallest. I mean, if we could do this verification in polynomial time, then we could just use the assumption NP equals P to actually compute, to show that P can be computed also in polynomial time. But this verification isn't obviously polynomial time, because if you want to verify a P is the smallest program, we need to verify that there isn't any smaller program that works. And that's like checking, does there exist a smaller program that works? And it's not clear how to do that in polynomial time. But actually, you can use the assumption that NP equals P once again to do this check in polynomial time. And once you're able to do that, then by using NP equals P a second time, you can find the smallest program in polynomial time. So I'm not going to go through this argument in detail, but it turns out that if NP equals P, then you can do compression efficiently. But of course, we don't like really believe, or many people don't believe, that NP equals P. I mean, our default belief is that NP doesn't equal P. What happens then? Is it the case then that the K superscript T compression scheme doesn't have efficient compression? And this relates to a central open question about cohomology complexity. Is K superscript T NP hard to compute? You've all heard about the concept of NP hardness. Satisfiability, clique, traveling salesman are all NP hard problems. And K superscript T seems like it should be an NP hard problem too. I mean, it's not hard to see as an NP, and it seems like a hard problem. It seems it should be NP hard, but we don't know that. And one of the main open problems in the area of cohomology complexity is K superscript T NP hard. And if it is, then it will be the case that NP equals P if and only if this K superscript T scheme has an efficient compression. It showed one direction here, and the other direction just follows if K superscript T is NP hard to compute. So if you didn't follow all the details of this argument, yeah, don't worry about it. That's okay. I like what I want you to really take away is that there's a strong connection to the NP versus P problem. And so this question about compression is closely related to NP versus P. And so this section of the talk, there are a few takeaways too. We defined resource-bounded versions of cohomology complexity. And that way we could get compression schemes that have efficient decompression and satisfy a version of near optimality. And whether they also have polynomial time compression is closely related to NP versus P. And then if it turns out that computing K superscript T complexity is NP hard, then actually NP not equal to P is equivalent to whether corresponding compression scheme for K superscript T has polynomial time compression. Okay, so like fundamental questions in complexity theory, such as NP versus P and is K superscript T NP hard, are tied to compression as well. Okay, so yeah, there's two sections of the talk left: learning and cryptography. So yeah, I guess I was like a little bit ambitious how much ground to cover, but because I'm not going too deep into technical aspects, this allows me to cover quite a lot of ground. So in the learning part, I'd like to focus on kind of a classical theory, but a very beautiful theory due to Santhanam, which kind of provides foundations for machine learning and kind of solve a solution for the problem of induction. So learning theory, as well as the process of doing science itself, is deeply concerned with the problem of induction. How do you extrapolate a pattern based on limited observations? You have some observations that you make, and you want to use that to kind of like to derive some kind of more general law. You want to generalize from it, and you want to be able to predict what happens in the future. And is there sort of mathematically rigorous way to model this? And Ray Solonoff showed how to use the tools of congruent complexity to solve this problem of induction in a mathematically rigorous way. And so compression is closely tied to this foundational question in learning theory as well. And I'd like to explain, at least in a qualitative way, how that works to you. So what's the setting? So what do we want to do? We have observations, and we want to try to discover a general pattern, and then we want to make predictions. So how do we model observations? We model them the most simple way possible as just a sequence of bits. We have some finite amount of data that we given as an observation. And let's just say that's an observed sequence X, which is a string of bits. And what does prediction correspond to? Let's think of like a possibly infinite sequence of bits that are revealed to us one by one, right? And at any point T, we've seen some portion of this X, and we like to predict the next part. And we want to continue doing this in a way that finally we are correct and we don't make any more mistakes, right? So we want to be able to extend the sequence in a meaningful way. And the assumption that we'll make, which is a very natural assumption, is that the sequence is produced by some deterministic computable process. So there's some algorithm that's running. We don't know what this algorithm is. And this algorithm is producing the bits of the sequence X and like, more and more bits. And at any point in time, we're only able to observe a finite number of them, and we want to tell what comes afterward. And this assumption that the sequence is produced by some computable process, that's kind of close related to the universal Church-Turing thesis, that things that processes that occur in nature can be modeled as computable. I mean, it seems reasonable to think that if our sequence is being produced in nature, then it's being produced by some computable process. Okay, that's great. But well, the challenge is that at any point in time, we only see a finite portion of this sequence X. So there's some finite part X that we've seen. And there might be many different ways of extending X, right? So, and how do we decide between them? So it might be that there's several possible computable processes that all first produce X and then extend it, but the extensions might be different for these different computable processes. They make different predictions. And how do we choose between them? And here
there's a question here about why the process is deterministic. Why is modeled as?
Yeah, that's a very good question. You can also model the process as randomized and kind of have a version of the theory that works for randomized processes. So this is not kind of because we're going to use Bayes' law eventually and Bayesianism eventually. So for simplicity's sake, I'm thinking of it as deterministic here, but you can also do it for randomized processes. So, and that might be somehow even more reasonable in terms of modeling what happens in nature. Okay, thanks for that. So yeah, we're going to be kind of like trying to explore this Occam's razor principle. What's Occam's razor principle? I mean, it's something that's been used in science like historically, which is that simple explanations are to be preferred, right? Like the simplest explanation is perhaps most likely. And the great thing now about congruent complexity is that it gives us a very, very kind of conceptually appealing notion of what it means to be simple. Simple can be defined to mean having low congruent complexity. So like if you think of this process, computer process producing kind of like an arbitrary long string, then the computable process with the smallest size code, so the algorithm with the that can be described as the smallest number of bits, should be the one that's preferred. So just as an example, if you consider the sequence 0, 1, 0, 1, 0, 1, 0, 1, and so on. Well, I mean, what should the next bit be? The most reasonable prediction is 0 because, well, if you consider a program which just keeps outputting 0, 1 over and over again, that's a constant size program and that will produce 0 next. But the prediction of 1 should not be ruled out either. I mean, there's a there's a more complicated program which, well, just repeats 0, 1 like 7 times, and then it then outputs a 1, right? There's some much larger program that does that. And that's possible. We just don't know until we've actually seen this bit. It shouldn't be ruled out, but we should prefer the prediction of 0 because that corresponds to a smaller size program. But how do we weight explanations according to the simplicity? And we're going to use Bayesian approach to do this. And this is like one of the deepest insights. This is like when you use Bayesian approach, you've got to define a prior distribution. And what's a good prior distribution to define? It turns out that there's this distribution that's a universal prior, like which is based on congruent complexity. And how do we define this? To generate an observation sequence of length n, you generate programs with probability proportional to 1 over 2 to the size of the program. So you generate a program P with probability proportional to 1 over 2 to the size of P. And then you run the universal machine on this program and get the first n bits and you output those n bits, right? So this universal prior is defined by random programs, by a certain distribution of programs, where a program of length k is considered with probability proportional to 1 over 2 to the k. That's a universal prior. And this has some nice properties, which I'm not going to go into now. And now we want to use Bayesian approach as follows. We want to compute the probability that a computable process P is, we want to find the probability that a computable process P is consistent with observation sequence X. And we can do it by using Bayes' rule by saying, well, what's the probability that X is produced by P? And then what's the probability of process P? Yeah, we can kind of, using universal prior, we can define the probability of P. Use Bayes' law to get the probability of P given X. So that's something that we can give get using Bayes' law once we've defined the universal prior. So that's going to allow us to weight different programs according to their likelihood of generating X. And then based on that weighting, we can tell which is the next bit of X likely to be, to predict. So some of those programs will generate a 1 next, others will generate 0 next, and you can weight them accordingly depending on the weights of these programs that we get from using Bayes' law. So Solomonoff induction provides a mathematically rigorous framework for induction. And there's some like really nice guarantees that come out of it. So for example, even though I haven't had time to get into it, like if there's some explanation of size, say R for your data, then you're not going to make more than R mistakes in predictions. Like eventually you'll kind of converge on the right explanation. And you're not going to make too many mistakes. The number of mistakes you're going to make will be related to the congruent complexity of your sequence. So there's like tight bounds that can be shown the accuracy of predictions according to this framework. And it's conceptually clean and insightful, and that it gives you this kind of information about what a good prior is and so forth, and how to use Bayes' law here and how to do induction. But the main issue is that this induction process is itself uncomputable because like computing the universal prior is not something that can be done by a Turing machine. And that corresponds to the fact that congruent complexity is uncomputable. However, by using sort of computable approximations of congruent complexity, like the resource bounded variance we've defined, Solomonoff induction has been implemented in practice, and it's been extended to reinforcement learning setting and so on by scientists such as Footer and Schmidt-Huber, like well-known AI people. So it's kind of like a corner of AI. I mean, it's of course doesn't receive the kind of attention that deep neural nets receive because it's just in terms of like the blow-ups in time that occur and so on, it can be quite prohibitive and you need to do things carefully. But conceptually, it's very interesting that this kind of induction does some implications for practice as well. So what are the takeaways here? I mean, like the main takeaway I think is philosophical, that congruent complexity is very useful for providing foundations for learning and for problem induction, for solving the problem induction in a very general sense. And this is done by using Solomonoff induction, where you use Bayesian learning together with the universal prior, which is directly inspired by the Occam's razor principle. And this gives you a very conceptually clean framework with mathematically rigorous guarantees. and some variances where have been shown to be useful in practice as well. So, I mean, there's much more to say about learning potentially, like there's a minimum description length principle, lots of other connections to learning. But yeah, this is all I have time for. And for the last 10 minutes or so, I'm going to talk about cryptography. Okay. Sorry, was that on the question in the chat? Or what is that?
No.
It's from before. It's from before. Okay.
Before, yeah.
Okay, so on the surface, it might not be obvious why crypto is related to the theory of compression. So the first thing I'd like to do is to say a little bit intuitively about why. So pseudorandom generators are an important primitive in crypto, and they're essential to encryption and other cryptographic tasks. And what does a pseudorandom generator do? It's a way of efficiently mapping short random seeds to longer pseudorandom strings. And these longer pseudorandom strings, you want them to be computationally indistinguishable from random strings. And that has like a very intuitive meaning. I mean, if you take any efficient algorithm and you feed it as input like completely random strings, and then you feed it instead as input like pseudorandom strings, outputs of this PRG, from its behavior, you should be able to tell any difference. Like the statistical distance should be small between what the algorithm outputs on random strings and what it outputs on pseudorandom strings. So that's what pseudorandomness is. Like you're able to stretch short random streets to longer pseudorandom strings that cannot be distinguished from random strings. And one very natural way to think of that is a sort of decompressor, right? Based on a compression approach or our theory of compression, a compressor and a decompressor. So think of the PRG as a sort of decompressor, like the short random seed is sort of the explanation of this longer pseudorandom string, or kind of compression of this longer pseudorandom string. So corresponding to this decompressor is a compressor, which just inverts the PRG, right? So if you can invert the PRG, then that'll be a way of compressing the outputs of the PRG. So in principle, we can invert the PRG. I mean, not efficiently, but yeah, it's possible to invert the PRG. And so that'll dramatically compress the outputs of the PRG, because from these long pseudorandom strings, you'll get back the short seeds. But this is something that you can't do to a random string, right? Like we know that random strings are incompressible just by counting algorithms. So no sort of compression procedure could possibly work for random strings. I mean, another way of thinking about it is that, in fact, the outputs of this PRG will have small cohomological complexity. We can show without too much difficulty, they have small cohomological complexity, while random strings have large cohomological complexity. So cohomological complexity distinguishes outputs of a PRG from random strings. So in a way, the security of a PRG relies on the compression not being doable efficiently. So we can do the decompression efficiently. That's how you define the PRG. But if you could also do the compression efficiently, if you compress the pseudorandom strings back to their kind of original random seeds, then that would distinguish random from pseudorandom, because when you apply this compressor to the output of the PRG, that would get you the short random seed, and you could verify that this is in fact the random seed that produced your string. When you apply this compressor to a purely random string, it won't do anything useful, because random strings just can't be compressed. So if you could compress efficiently, we'd be able to show the PRG is insecure. So in particular, if the PRG works, that means that compression isn't doable efficiently. So that gives you kind of a close link between pseudorandomness and compression, that the existence of pseudorandom generators imply that compression isn't doable efficiently. So pseudorandomness implies the hardness of compression. And now it's natural to ask, that can you go in the other direction? Can you actually base pseudorandom generators, which are, after all, objects that are very useful in practice, can you base them just on the hardness of compression? And a very recent line of work, originating with a paper by Liu and Pass, but in which I've been involved in as well, aims to do precisely this by basing PRGs. And in fact, what they do is to base the equivalent notion of one-way functions, which are fundamental cryptographic primitive, not to be equivalent to PRGs, on the average case hardness of the time-bounded variant of cohomological complexity we already defined and consider K superscript T. So I just want to tell you like a couple of things about these results before finishing. So first thing I want to explain to you is what average case hardness is. I mean, you might have seen this before, but in case you haven't, Typically, complexity theory deals with worst case hardness, where computational problem is considered hard. If there's no efficient algorithm that solves it correctly in all instances. But this notion of worst case hardness is sometimes problematic because the hard instances for an algorithm, the instances on which algorithm fails, may be rare or they may be hard to find. And in those cases, worst case hardness isn't very relevant. We'd like to know what happens on typical instances. I mean, average case hardness, which is studied intensively by Levin and Paolozzo and others, instead studies hardness with respect to distributions on inputs. And a problem L is considered to be average case hard over distribution D if no efficient algorithm solves L correctly with high probability on instances sampled from D. So you sample an instance X from this distribution D, and then you apply the algorithm to that instance. And if it solves L correctly, it's good on average. If it doesn't solve L correctly with some noticeable probability, then it's not a good average case algorithm. So this is sort of like a nice way of looking at hardness on typical instances rather than worst case instances. And average case hardness is a kind of hardness that's somehow more natural when you're doing cryptography. So you recall that the K superscript T problem is problem computing the T time-bounded complexity of a string. Now, we want to consider the average case hardness of K superscript T problem. And what do you mean by average case hardness? You got to specify a distribution if you want to make sense of the notion of average case hardness. One very natural distribution is a uniform distribution, and that makes sense for K superscript T. I mean, we know that like random strings are likely to be very hard, but yeah, but still in terms of computing the Kolmogorov complexity exactly, that might still be hard to do. So hardness of the uniform distribution is natural to consider. But more generally, we would consider hardness over any sample distribution, namely a distribution sampled by a polynomial time algorithm. And remarkably, both of these notions of hardness lead to equivalences with existence of PRGs. So the question I asked before, can PRGs be based on average case hardness of compression, turns out to have a positive answer. So there are these two theorems, Liu and Pass from last year, who show that PRGs exist if and only if K superscript T is hard over the uniform distribution. And a theorem of mine with Rahul Elango and Anlin Ren, which is that PRGs exist if and only if there's a samplable distribution D such that K superscript T is hard to approximate. By approximate, I mean to like a term that's slightly larger than log n. So yeah, fairly good approximation. If this is hard to do, then if and only if PRGs exist. And in fact, quite extraordinarily, you can replace K superscript T here by Kolmogorov complexity, and you would get essentially the same result. I mean, there's like a minor condition I'm hiding here for K superscript T, but for Kolmogorov complexity, this is actually an equivalence. If you ignore the T, this is actually an equivalence proved in a paper. And these results are the first ones to give equivalences between PRGs and hardness for natural problems. Example, K superscript T and Kolmogorov complexity. And it's well known for a long time that the hardness of problems such as factoring, learning with errors, lattice problems implies existence of PRGs, but these implications are not known or perhaps even believed to be equivalences, while here you actually get equivalences with the hardness of natural problems. So what are the takeaways here? There's an intuitive link between pseudo-randomness and compression as well. We already saw like links between complexity and compression, between learning and compression, and now there's links between pseudo-randomness and compression as well. And this comes from the fact that outputs of PRGs are compressible in principle, but the compression needs to be intractable in order for PRGs to be secure. And in very recent work, this intuitive link has been turned into formal characterizations of pseudo-randomness in cryptography by average case hardness of problems, just K superscript T and congruent complexity. Okay, so coming to the end of my time slot, so just a conclusion. Motivated by the goal of creating a theory of compression for individual strings, we define congruent complexity and its variance. And these notions are sort of philosophically deep. In fact, the philosophical aspects of them have been studied quite a lot as well. I didn't go into that very much. They have relevance to fundamental problems in many areas of computer science, including complexity theory, machine learning, cryptography, and they also lead to intriguing open problems. So let me just mention a couple. The first is just repeating an open problem I mentioned before, is K superscript T, NP hard to compute for polynomially bounded T. This would be very interesting to know. And it would also sort of like show kind of a characterization of the NP versus P problem by compression schemes that associated with K subscript T. And the other problem is like our original motivation, right? There are these three constraints we want to satisfy: optimality or near optimality, efficient compression, efficient decompression. Are there near optimal compression schemes that satisfy efficient compressibility and decompressibility? I think that's unknown. I don't really know strong results in that. It'll be interesting to know more about that. Thank you.
Thanks a lot, Rahul. That's a great introduction to the area. So I have a couple of questions which I'll ask you, and maybe if others have questions, you can type it in the chat in the meantime. Do you see the equivalence of the average case hardness of the KT problem to PRGs? Do you see it as evidence that this problem may not be NP hard? Or what do you think of that?
Yeah, I tend to see it as evidence that you can base one-way functions on NP not equal to P, or at least in average case hardness of NP.
Okay, so it's the other way.
Yes, I see it as evidence that that heuristica and precedent don't exist. But yeah, maybe some people they might be skeptical about whether these problems are NP hard. It's just that there's no real strong evidence that these problems are not NP hard. I mean, there's some evidence that they're not hard with respect to limited kinds of reductions. But like as you are aware, there's like a lot of work on the weakness of non-adaptive reductions in terms of basing one-way functions on NP hardness. But yeah, we know much less about adaptive reductions. So it could be that adaptive reductions are much more powerful. And
even those reductions, aren't they specific to like worst case NP hardness? They don't say anything about average case, right? So they shouldn't really
come. Which reductions?
You mean like Dakavia, Goldwasser, that one?
Yeah, and they say exactly. So like you're saying, the negative results are in any case about worst case, basically on worst case NP was P rather than average. Yeah, that's true. But even those results, I mean, I'm saying that they're all like about non-adaptive hardness, or like there's Bognor-Bruska paper, but that's also about kind of like there's conditional one-way functions that consider, I think. And it could be that adaptive reductions are much more powerful. In fact, like based on other results I know in cohort complexity, I would guess that adaptivity is quite powerful here. So there's no reason to believe that K-poly is not NP hard with respect to randomized adaptive reductions. And in fact, like recent results by Longo sort of like on the hardness, the conditional variant of the problem, NP hardness, the conditional variant of the problem. He has results on the ETH hardness of the minimum formula size problem, and so on. So there's like other kinds of evidence that these problems might be worst case hard in some sense, not quite NP hard as yet, but there's progress towards showing stronger and stronger hardness results. So yeah, it's a challenging problem because like constructing a reduction sort of like in itself sort of tends to create instances that have small complexity, but there are ways of using randomness or adaptivity to overcome that, which maybe haven't been explored in enough depth. And so yeah, as far as I can see, there isn't clear evidence that it's not NP hard. My own feeling is that it probably is. I mean, so there are like two ways in which it could be NP hard. It could just be that there's like a standard like adaptive randomized reduction that shows as NP hard, but it could also be like non-black box NP hard, and that we might be able to show that NP that K superscript T in BPP implies NP in BPP without actually giving a reduction.
I see. Okay.
And those kinds of like implications, I think, like win-win analysis and other non-black box techniques in cryptography, because these meta complexity problems and K subscript T are so related to cryptography, it could be the techniques of those sort come in useful. Yeah.
Okay. Yeah, I'm looking forward to what will come out of this.
Yeah.
And do you think this problem may go beyond one-way functions to stronger cryptographic primitives?
Yeah. So I mean, a very sort of natural connection that we could draw is with indistinguishability obfuscation, because I mean, there's like there's this sort of like work it goes back a few years by several authors showing that if NP doesn't equal to P and IO exists and one-way functions exist, and so that's sort of like ties IO to one-way functions, and now because one-way functions are tied to congruent complexity, it sort of also connects, I guess, congruent complexity with IO. But there might be like much deeper connections, like XIO. I mean, from the surface of it looks quite a lot like these meta-complexity notions. So I would guess that with IO, I mean, though as I'm far from being an expert in crypto, but just from my perspective, it seems that IO is a possible application domain, and public key crypto as well. Actually, argument systems. I think there's lots of potential directions. So lots of scope for establishing further connections. Yeah, somehow like these meta-complexity notions, in the worst case, are very like intractable. In the average case, they're more robust and seem to be quite closely tied to cryptography. And I think there are many more connections of that sort to be uncovered.
Yeah, especially like you said, obfuscation, right? Because it also explicitly talks about representations of the programs.
Yes, yes, exactly. Yeah, yeah.
So there's another question here. The question is: are there complexity classes related to congruent complexity or time-bounded congruent complexity that have been characterized in descriptive complexity theory?
I see. Yeah, I'm not like completely sure whether by descriptive complexity the questioner means like finite model theory and like area like that, because that's what I mean. Descriptive complexity typically relates to like a finite model theory sort of domain where you're trying to define structures using like sentences from like a certain vocabulary, and considering this class of structures to satisfy a sentence and so on, which was an active area, and it is still like an area that connects quite strongly to verification, but hasn't seen that much progress from a theoretical point of view in very recent years. I mean, in kind of specific questions there have been progress, but on the fundamental questions there hasn't been much progress. And yeah, there's not aware of many sort of links with congruent complexity, but yeah, it's quite possible that there are. Yeah, that's. I think there's probably more links in the computability domain. Because congruent complexity is uncomputable, you could look at like the Turing degrees of congruent complexity, and there's also these links to the foundations of probability, which are somehow also associated with some of induction and so on. So, like, if you don't impose any resource bounds, I think what the questioner might be looking for, one suggestion is to look at these connections first in the unbounded domain. I mean, a general sort of recipe for looking at connections is sort of first see what happens in the resource unbounded domain, and then look to see how things get more complicated in the bounded domain. I mean, usually these questions are simpler to answer, and these connections are simpler to draw in the resource unbounded domain, like just plain congruent complexity or time-bound complexity. But yeah, the question about complexity classes, yeah, it's a nice. I mean, yeah, I think like, I mean, I strongly believe that these problems are NP hard, and some other researchers do too. But of course, there's like connections to like classes like zero knowledge. It's known that like various meta-complex problems are hard for statistical zero knowledge. So there's relationships to those classes. There haven't, as far as I know, been attempts to define complexity classes specifically to do with congruent complexity, except for some recent attempts to look at like explicit construction problems, like problems where you're trying to compute some answer satisfying a particular property. And there has been some work recently by Oliver Cotton and others where they look at TFNP classes, or like generalizations of TFNP, and look at the role of congruent complexity there. And so there's a paper in Fox this year, and there's one from ITCS, and so the paper from Fox is just by Cotton, and he looks at problems that are very close related to congruent complexity and shows that they complete for a complexity class of function problems, of total function problems. So that's one context in which it's been done, but maybe there are others. Yeah, interesting question.
Another question: do you think there is like the learning techniques based on sort of prediction you're talking about, right? The ones that people are actually implementing now? How far do you think that they will go, like the approach to learning based on compression?
Yeah, I mean, like, I'll just be cautious and say that they're conceptually very interesting. In terms of how far they'll go, it's very hard to predict. I mean, like, neural nets was kind of stuck for 20 years and then it just exploded. So like one never knows, but I mean, like the kinds of optimal search techniques where you're always like doing some systematic search over small descriptions, it seems like there's always going to be a blow up there. But maybe like these descriptions, you could kind of like do it more cleverly by using, I don't know, like state-of-the-art tools like deep learning or something, rather than and learning representations in that way rather than just enumerating over them. But I have very little intuition for that because I haven't really like worked in a practical way with machine learning. So it's hard to predict, but I think it's if it can be made practical, it has like a lot of potential because it can do things that go far beyond pattern recognition, I think. So that's one of the great kind of potential benefits of doing things that way. Well, I think like neural nets, even though they're so powerful, many of the tasks they solve are like pattern recognition tasks. So this sort of like things like program learning and kind of universal search are go far beyond that. But yeah, the implementation challenges are enormous. Yeah.
Okay. Don't seem to be any other questions. I have a lot of other questions, but I'm not going to ask them now.
Feel free to send me email about them.
I probably will.
Okay.
Thanks again for the talk. This is great. And hope to run into you sometime in person. At some point.
Yeah.